Okay, the purpose of this video is to cover the next goal. Before watching this video, make sure you have a good understanding of finding a confidence interval for means, including the standard error, which was standard deviation of the sample over square root of n, and the use of the t-distribution or t-curve that was talked about in the last video that was developed by that guy Gossett. So that video was long, but basically to do any more inference with means, you have a good grasp of all those concepts. So make sure that those are things that you're comfortable with, because I'm going to be referencing them in this goal. Also make sure you know how to create the confidence interval, because basically this goal follows like we did with proportions. Remember, with proportions, we also found confidence intervals. And then to find a confidence interval of a certain width, like with proportions, if we wanted to be within plus or minus 3%, there was a way to figure out how many people or items we'd have to sample to have that level of error at a particular level of confidence. So if we were at 95% confidence and we want a plus or minus 3% margin of error, there was a way to calculate how many people or how many items or what your sample size would be to find such a thing. So this is an analogous lesson for means. Basically, we have the same issue with means. If we want to create a certain confidence interval, and we'd like to have the confidence interval, say, at a certain level of confidence and within a certain range of the mean. Now, we're not doing proportions, so it won't be plus or minus a percent. It'll be plus or minus an amount. So maybe I want to know what's the average height of a freshman guy in JC High School, but I want it within plus or minus 1 inch, so I don't want much error. I want to be within plus or minus 1 inch. And say I want it at 98% confidence. That's going to require a certain sample size to get that level of error at that level of confidence. So we want to talk about how do we get such a thing? How do we get that number that we need? It ends up being a little more complicated due to that t-distribution. All right, so hopefully that gives you an overview of this goal, which is be able to find, for means, the sample size needed for a desired margin of error. All right. To remind you of the confidence interval formula for means, remember you need a sample. From that sample, you can get the sample mean and the sample's standard deviation. With that, you can get the standard error using the sample standard deviation. So this was the formula I said to make sure you were comfortable with, because when you make that confidence interval, you need your sample mean. You're going to do plus or minus. I forgot the minus again. Let's get that minus in there. I think I copied it off of the one from before. All right, there, now it's correct. We want plus or minus, and this part, just like with proportions, this back part's called the margin of error, because basically we're using our sample mean as a point estimate, and then we're allowing ourselves to go so far to the right and so far to the left to capture the real mean. Remember, that's the whole goal of a confidence interval, is to use the sample mean to hopefully sort of cast a net of this size that within a certain level of confidence should have the real mean, the population mean in it. So if I want to know how tall freshman males were at Johnson City High School, I would find a sample of them and then extend the range this large around the sample. And I would, so long as I use the proper confidence level, I could be 98 or 99 or 90 or whatever percent confident that around there was the real average, the average for all of the people, not just my sample. All right, so we're going to be talking about when we need a certain number of people. The number formula is actually hidden into this. Remember, the standard error is s over square root of n. All right, so the n is hidden in this formula, and we want to find what that n value is. All right, so we have x bar plus or minus t sub n minus 1 star, standard error of the mean, all right? And that's our margin of error. So we have to determine our needed sample size. Larger is better. We always, the larger the sample size, the lower or the smaller our confidence interval needs to be. But remember, there's an issue, same thing we ran into with proportions, is that if we make our sample size too large, we can end up running into the problems of expense or difficulty obtaining that kind of sample. So we saw with proportions, it was common to use 500, 1,000, at most 2,000 because it was doable without too much expense and too much time. So the larger the sample, the better the results, but there's a point where it becomes very cumbersome or expensive to be able to get the sample size that you want. So it would be better to sample 1,000,000 people instead of 1,000, but 1,000,000 people is a lot harder to basically coordinate or find or do in time. So basically we need to come up with this balance. So we want the smallest sample size that we need to do the job. We want to be efficient. So if somebody wants a certain margin of error within a certain confidence interval, we don't want to have to ask any more people than what's necessary. All right. So remember the margin of error. So from this formula, the margin of error is this back part. I just replaced the standard error formula with its version that we have to approximate. The standard error is actually sigma over square root, or sorry, standard deviation is sigma over square root of n. But remember, we normally don't know sigma. Sigma is the population standard deviation. S is the sample standard deviation, which is what we have most of the time, because if we take the sample, we can find its standard deviation. The population, we usually don't know the value of. So I'm just going to talk about the back part of that formula, the margin of error. And we're going to want a certain margin of error, and we're going to want to know how many people or how many items are needed in order to get that margin of error. Now, the problem we run into is before we take our sample, there's going to be a bunch of stuff we don't know. Since we haven't taken the sample yet, we clearly are trying to look for how big to make the sample. So that not only makes this unknown, but it also makes the t-curve we need to use unknown. And that's a problem. We didn't run into that before because we used a normal curve and the values were set. Unfortunately, we have to use a t-curve to do these means inferences, and that runs into a problem because we're not sure what t-curve to use without knowing our sample size. So already we run into a pretty big problem because we don't know this or know this. And since we haven't taken our sample, we also don't know this. So at first it starts off like we can't even find this because basically we have none of this information when we start because we basically need the sample to do it, and we don't know how big to make the sample. So that's what this part says. Certain parameters are unknown beforehand, like the degrees of freedom we need for our t-curve and the sample standard deviation because we haven't actually taken our sample. So we need ways around this. What they do in real life is for the sample standard deviation, you can use a reasonable guess, or you can use another study or take some samples yourself beforehand. Basically, you just need a number that's reasonable. So in the problems, a lot of times, they'll mention somebody came up with this. Now, and they'll give you some kind of standard deviation that's reasonable. In real life, you would try to, once again, if no other information was around, just go with a best guess of something that was reasonable. But normally what they do is use another study or just take a sample itself just to get a rough idea. So if you took a couple samples, so you might be taking doing a little bit of extra work, but if you took a few samples, even if they were small, you could start to get a feel for what the standard deviation was. So luckily for you, you're not doing these from scratch like a professional would. So they normally will give you some kind of information about what the sample standard deviation either should be or something that someone else found that's reasonable to use. All right, so we're not really going to have to worry about the S, but we still are going to have to worry about this N because we're going to find N, and that still doesn't help us know what N minus 1 is. All right, so to handle the t-score problem, here's what somebody figured out. Remember that the t-distribution and the normal distribution, so a t-score comes from the t-distribution, a z-score comes from the normal distribution. If the sample size is large, so say you need a lot of people or items in your sample, well, then the degrees of freedom on the t-curve will be high because you just do n minus 1. So say you needed 100 people, you would basically have a t-curve of 99 degrees of freedom. And remember that the higher degrees of freedom, the closer you are to a normal curve. So basically for a really large needed sample, the t-curve and the normal curve will be almost exactly the same, nearly indistinguishable. They had to put a cutoff because the t-curve is never exactly the normal curve, but it gets to a point where when you get high enough, they're essentially, for this purpose, indistinguishable. But remember, if the degrees of freedom's low, meaning if the sample size needed is low, then the t-curve will differ significantly enough from the normal curve. So I had talked about that in the last video, and that's what I was saying. Make sure that you understand that concept of the t-curve, because basically the t-curve is a shorter, fatter version of the normal curve, and if the sample size is low, the t-curve is considerably shorter and considerably fatter on the ends than the normal curve. So the cutoff they decided to use was 40. So basically, if you do the procedure I'm going to show you, and you find your sample size is bigger than 40, you could just leave your answer. If you find the sample size is less than 40, you're going to run into trouble. Now, how are you going to find it? Basically, you're going to use a z-score instead of a t-score. So that's what this is saying. For a t-score, don't use the t-score, use what the z-score would have been. So instead of t-star, we'll replace it with z-star. So going back up to the formula, instead of using t-star, I'm going to get an estimate using z-star. All right, so that's what this last part says. Basically, you're going to replace z with t. If the number comes out high, then z and t are essentially close, so you could just use that number. If the number comes out low, less than 40, the z-score is giving us a rough estimate, but it's somewhat off. We can use that to go back and get a better estimate using a t-distribution of that number of degrees of freedom, all right? So in the examples, I'm going to show you doing this process, but realize it's a little more complicated because we're going to have to not only come up with a reasonable guess for S, the standard deviation of our sample, but we're also going to have to kind of cheat by using a z-score to come up with an estimate, and then depending on the size of that estimate, we may need to recalculate using the proper curve, all right? So the best thing to do going forward, like I said, if this doesn't quite make sense, look at the examples, and hopefully it'll make more sense, and then you can come back and the things I'm going through should make more sense after seeing them gone through an example. At least I hope so. All right, so let's look at two examples. So the first example is for a website. They say the download times from a website with hit movies claims that there's a 30-minute average for the download of the movie. They advertise 30 minutes, but once again, most of Inference is about seeing if such claims are true. So they claim 30 minutes, but is it true that it only takes 30 minutes? So in order to come up with a sample, we would want to know how many of these movies should we download to come up with a reasonable X bar and then make a confidence interval. So I'm not actually going to make the confidence interval, but we want to know if we want a certain confidence interval, and that, how would we get it? And that confidence interval, we could see, does the confidence interval have this value in it, or is the confidence interval maybe higher? Say the confidence interval is too high and doesn't contain this, we might have evidence that they're over-exaggerating their downloads, right? So basically, we're not actually going to test the claim. We just want to figure out how big should our sample size be to be able to come up with a confidence interval of a certain specificity, which it says below. So the first thing we need is some kind of good guess for the standard deviation. So here they just tell us someone tries a few downloads, and they come up with a reasonable guess that the standard deviation of downloads is about 10 minutes. So that means, you're going to have a certain amount of time that it takes for a download to happen. Per download, it's not uncommon from person to person, computer to computer, whatever, for, within one standard deviation, there to be a 10-minute swing on the download times. So now the question is, if we want to test this claim, how big of a sample size should we use to ensure that we're at 95% confidence and we have a margin of error of, I should have changed this back. I'm going to use 8 minutes because 4 we could calculate, but 8 makes my point better. All right, so sorry about that. I should have changed that. So we're going to use 8 minutes. So they want a margin of error of plus or minus 8 minutes. Now, actually, the reason I changed this is because 8 minutes seems pretty wide, right? If you're going to make a confidence interval, you're going to go 8 minutes up and 8 minutes down. Now, when I did shrink it to 4 to see how it turned out, but it didn't make the point I wanted to make as well. So that's why it was 4 before. Actually, the original example was 8. So I'm just going to stick with 8, all right? So 8 should make the point pretty well. So what I'm going to do is, ignore that 4, make sure we're going to go, we want to basically be 8 above or 8 below with our confidence interval, and we want our confidence interval to have 95% confidence, meaning if we did this procedure over and over and over and over again, 95% of our confidence interval should contain the real value, all right? So how do we get this magic number? Like, how many downloads should we make? Because we don't want to sit here and do more downloads than we have to. You could do 50 downloads, but that could take you a long time, right? Especially since the downloads could be 30 minutes or more. According to this, it wouldn't be uncommon to get a 40-minute download or maybe even a 50-minute download. So the idea is we want to do as few of these downloads as possible to test this claim. So what do? Well, we look at the board, and I'll explain what we need. So the upper right panel here just has the information that we know and the information we don't know. We know the sample standard deviation. They told us a reasonable estimate was 10 minutes. So our samples come out with a 10-minute standard deviation. Once again, that's not the population one. It's just how samples come out. The N is what we're looking for. We don't know how many downloads to make in order to get that level of confidence with that margin of error. So the N is what we're looking for in the problem. Now, the problem we run into, since we don't know N, like I mentioned before, we don't know what T star to use. At 95% confidence, we would normally calculate a T star like we did in that last video for the confidence interval. But without the N, I don't know what T curve to use. So this is where we do the cheat I was mentioning about. We won't use T star. We'll use a normal curve instead. We'll use a Z star. It'll be an approximation, and we'll see how it works. The margin of error that's desired, which, remember, I changed. The margin of error desired is 8 minutes. All right, so we want when we make our confidence interval for it to range out 8 minutes up and 8 minutes down from our sample average, and see if, in the end, if that captured that value 30 or not, to test their claim, all right, to come up with the actual confidence interval for the true download time and see if it matched what they said. All right, so these are all the parameters that we're going to use. Now, so on the left shows doing this calculation. The margin of error formula is actually T star N minus 1, sample standard deviation over square root of N. The sample standard deviation, we're using 10. Now, this is where the cheat comes in. I need to find N. So instead of using T star, I'm going to use Z star. Now, Z star can be determined because we know the level of confidence. So these were from before. Remember, if we're using a normal curve and we're at 95% confidence, we need to go 1.96 standard deviations out. So this was a number I had said before, it's good to memorize. If you don't know that, remember the procedure to find it would be to take this level of confidence, 0.95, cut it in half, which would be 0.475, add 0.5 to it, which would turn it to 0.975, and then do inverse norm in your calculator of that number. And it'll tell you, in order to cover 95% on either side, how far you'd have to go out. You have to go out 1.96 standard deviations, or a z-score of 1.96. Now, going forward, the 1.96 is not the t-score, it's the z-score. So it's off somewhat. Remember, the t-curve is a little shorter and wider. So to go out as far on a t-curve would have to actually be farther than this, because the t-curve is shorter and fatter. So to cover 95% is actually going to be more than this. But remember, we don't know what t-curve to use. So this is just an estimate to see what happens. All right. So from here, this gives me enough to solve it, because I'm fudging it with the z-score using the standard error that we determined, or sorry, not the standard error, the standard deviation from the sample that we determined to get the standard error. And then now n is the only thing left. So what is the sample size under the scenario? I went through and solved it. So I multiplied these two together. 1.96 times 10 is 19.6. And then this can be solved by cross multiplication. If you keep going, you'll get the number 6.0025. All right. So the rest of the solving is basically just dividing that 8, and then to get rid of the square root, you square. Now, here's where you, in this case, have to go on, but in other scenarios, you might not have to go on. So let me explain why we need to go on this case. Remember, I had mentioned that if the sample size was bigger than 40, the t-curve and the z-curve, or the normal curve, would essentially be so close to the same it wouldn't matter. So if this number had come out bigger than 40, we would just have that as our answer. So that's important, because that's not what's happening here. So if this were bigger than 40, you wouldn't do any more work. You just go, okay, well, since it's such a large sample size, I use the z-score, but the t-score would have come up with something almost essentially the same, very, 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 very close. So there's no reason to change this number. All right. Now, the problem for me is that's not what happened. This isn't bigger than 40. Since it's less than 40, it's low. And what that means is the t-curve is different enough from the normal curve that the estimate isn't all that great. We need a better estimate. So this says it's low. We need a better t-curve estimate than what the z-score gave us. So here's how we make the better estimate. Now we have a rough idea of the sample size. It's not great, but it's better than nothing, right? This said use a sample size of 6. And it's got that 0025 on it. It's really close to 6, because a lot of times you might round up. But in this case, it's so close to 6, I'm just going to go with 6. So then here's what you do. You recalculate, but now you have a better idea of the sample size. The sample size is low. It's around 6 makes a t-curve that's a better representation of what's going on than this normal curve is. So what you do is you go back and you recalculate it. You recalculate now with the t-curve using this number as your estimate. So sample size is now going to be 6. So now I can use a t-curve with 6 minus 1 degrees of freedom, or 5 degrees of freedom. So that's what I'm showing here. I'm just recalculating this formula using this information for sample size. And it uses a t-curve now that's better fit to the data than the normal curve was, and it comes up with a better answer. All right, so recalculating, the margin of error is still 8. I'm going to use a t-curve with 5 degrees of freedom, and I'm still going to use that standard deviation, sample standard deviation of 10 to find n. So now, how am I going to get the t-star with 5 degrees of freedom? Well, same way I would have gotten the z-star. Now, you have to do in this case, because with the t-curves, all of the values are different. You can't just cheat with like, oh, I know it's 1.96. That only works for the normal curve. So what I show here is what you should do in your calculator. You want 95% confidence. Cut the 95% in half. So 0.95 cut in half is 0.475. And 0.475 plus 0.5 is 0.975. Now, what's the t-score associated with this? Do inverse t of 0.975 with 5 degrees of freedom. So instead of giving you the normal curve number, which was 1.96, remember the t-curve for low degrees of freedom is fatter, it actually gives you a better range. It says you should go out 2.57 standard deviations on that kind of t-curve. So this gives us a better estimate than having used the normal curve. So with large degrees of freedom, these numbers would have been close. But since the degrees of freedom are small due to the sample size coming out small, these numbers are significantly off. So it's better to use this number. This number is way closer to the number we should use than this number is. So now that we have a much better estimate, we'll calculate again. So now that I know to go 2.57 standard deviations out, once again, I multiplied this by the 10, got 25.7, cross-multiplied, divide the 8, and then squared the square root of n. And that gave me 3.2125, which when I squared came out 10.32. Now, just to be safe, if I rounded it down, I want the minimum that's going to be guaranteed. So since I do have that 0.32, I'm going to round it up to just guarantee that it's going to have that margin of error. So rounding it up is 11 downloads. So this is the final answer. How many downloads should I perform in order to be able to make a confidence interval that has a margin of error of plus or minus 8 that will capture the true value 95% of the time, or have 95% confidence? It should be 11 downloads. If I do 11 downloads, I can create that confidence interval that they want. And like I said, we're not actually going to create the confidence interval in this problem, but if we did 11 downloads, we could create the confidence interval with the desired margin of error that they want with the desired level of confidence. All right. Let's look at one more example. I would recommend, it's very similar to the other one. I'd recommend you try it. See if you can identify all the parameters. It's very similar to the other problem where they do give you a sample standard deviation to use, a good guess. They give you the level of confidence, and they give you the margin of error that's desired. So if I were you, I would take a moment, see if you could calculate this on your own. I'm going to go ahead and just show the answer now. All right, so hopefully you'll stop and get what I'm about to get. All right, so let's take a look at how many people we should sample. So in this case, you should sample 20 people. Here are the parameters. Once again, so I have the same structures before. They said the sample standard deviation was 2.5 inches. The margin of error desired was to be within one plus or minus 1 inch. They only want 90% confidence. And once again, since we don't know the sample size, we can't know the t-curve. So we'll use a normal curve to start it off. So like before, here's my margin of error formula. Instead of using T star and replacing it with Z star to at least get a rough estimate, S is 2.5. The margin of error is plus or minus 1. I didn't mention this before, but you don't need the plus or the minus. You only need the plus because once you find the positive version, it would come out the same for the negative version. If you had made this negative, when you go and square it, in the end, it doesn't matter whether it was plus or minus. So even though the margin of error is plus or minus, we only need the positive version. I don't think I mentioned that. So it's a little technicality. You just need the positive version of it. So that's the margin of error of 1 inch. Now, the Z star for 90% is one of those ones you should have memorized, 1.64. Once again, if you don't have that memorized, cut 90% in half, you get 0.45. Add 0.5 to it, you get 0.95, and then you do inverse norm in the calculator, and it'll generate this number for you. I would memorize these numbers, though. They're very handy for when you take your exam. So then I did the math and solved it. Similar to before, I multiplied these together, and then cross-multiplied, and then squared. And then this time I get 17. So if I had used a normal curve, I would need 17 people. Once again, it's too low. So I stress this because I wanted to do the harder examples. I didn't do an example where we didn't have to go further. Remember, if this number's bigger than 40, you can stop and use that as your answer. I wanted to give you a chance to do the harder version, so it didn't come out big enough. Once again, this is still under 40. It's too low, so the rest of this is necessary. So I will say it again. If this were bigger than 40, you're done. You don't have to go back and do this. In fact, if you went back and did this, you'd find that the answers would be they'd be the same, and it would have been a waste of your time. So since this is under 40, I'm going ahead and recalculating because 17 is not quite the right answer. In fact, you can already see it's supposed to be 20. So 17 is not quite good. So what we'll do is we'll go back. We're going to use this 17 to use a t-curve that models this better than the normal curve did. So same formula, use the margin of error formula, but now use 17 as your sample size. Remember, 17 minus 1 is 16 degrees of freedom. So I'm going to use a t-star, and I'm going to use it on a t-curve with 16 degrees of freedom. How far should I go out? Well, I need to go out further than 1.64. I need to actually go out 1.75 on this better t-curve. Now, how do I know that? Well, I showed it once again on the right. I took 90%, cut it in half, and then added 0.5, and that gave me what to put into the inverse t. I should do inverse t of 0.95 with a curve of 16 degrees of freedom. So when I put that in the calculator, that's where I'm getting this 1.75. In order to go out 95% on either side of that t-curve, I need to go out 1.75, which, once again, is larger than what I would have to do on the normal curve. That's why this is a better approximation due to the low sample size. All right, so I did the math, multiply these, cross-multiplied, squared, and got that the n was 19.14. Once again, I don't want to round it down because I'm risking not quite being within. I'm going to the wrong side of it. So it's better to round it up and just be guaranteed. By going and doing the sample of 20 people, I will get what I want. So once again, what do I want? I want, when I take my sample, to be able to create a confidence interval that at 90% confidence will give me the true value within 1 inch plus or minus. So if I sample 20 people, my confidence interval will have the correct width. It will tell me the true value within plus or minus 1. And it will do that at 90% confidence, meaning if I did the sample over and over and over and over again, 90% of my samples should contain the true value. So when we do this procedure, we're pretty likely to get a confidence interval that covers the real value within plus or minus 1 inch. So then we'd be able to know what we think about this unusually tall tribe. We could take the sample and see, do they truly come out unusually tall, whatever that is. I guess we know averages in the United States, like men are about 5'9.5". I think women are 5'3.5" or 5'4". If this tribe is unusually tall, maybe we'd find that their average is considerably larger. So maybe the men are 6 foot tall and the women are 5'8" or something. And we would be plus or minus an inch, but we could then see if those numbers I said were true, it would be significantly higher. If they came out, the men came out 5'10", we might say, well, within plus or minus 1, the American men are in that range too. So perhaps they're not unusually tall. Same thing for the women. Maybe they come out 5'4.5", and we're like, well, plus or minus 1 inch would be what the true value is. And American women are in that range, so they're not unusually tall compared to people in our country. All right, so this was about finding sufficient sample size. I'll put up the assignment, and I stress again, check this number. Over 40, don't go ahead and recalculate. Under 40, redo this procedure and get the proper value. All right, until next time.